Hi there, and nice to have you back for our discussion of Advanced SQL. So if you recall, we were talking about set returning functions. So functions built into PostgreSQL, and we have met many built-in functions already in our discussion of the previous topics. And I think several times already, I've mentioned that, hey, this is a built-in function. You can also have user-defined functions. Okay, and let's devote the next few minutes of this video to the discussion of user-defined functions in SQL. There are several flavors of that. The first flavor should be the topic of the next few minutes. This is about user-defined SQL functions, or UDFs. So a user-defined SQL function is characterized by the fact that the body of the function, so the body of the function, so everything between these dollar signs, we will talk about the syntax in a minute, is actually implemented in terms of SQL queries or SQL DML statements. There are other flavors of UDFs, or user-defined functions, in a SQL system. One flavor is the PLSQL function, the programming language / SQL functions, which will also play a role near the end of the entire course. And there is the possibility to use your favorite programming language, for example Python, to implement your own functions and integrate them very tightly and neatly with the rest of the SQL system. These are not in focus right now. We will talk about SQL functions. The body of functions is itself defined in terms of a sequence of SQL queries. All right, so the syntax is shown here on the slide, and I think it does not have too much to surprise you. We are talking about creating a function named f with k parameters, so this is a k-array function, and it will return a value of type tau. So all of the return type and also the type of the arguments, of the k arguments here, are the members of the regular type system of PostgreSQL. There are some restrictions there. We will come to these in a minute. The body itself is specified between two delimiters. You see that I've used these double dollar signs here as delimiters, and I think that would be a convention. But we have seen the double delimiters before, and you could have arbitrary but identical strings between these double delimiters if you so choose to make these stand out more or convey some information to the readers of your functions. But I think I will stick with the plain double dollar signs here. All right. Inside the dollar signs is the body, so a sequence of SQL queries and DML statements separated by semicolon. Okay, these are executed in sequence. So Q1 is executed first, Qn is executed last. The value of Qn, the last query, defines the return value of the function. So the return value of Qn and tau, they should match indeed, because this is what the function promises to return. If all the functions in the sequence are indeed read-only queries, so real SQL queries, not DML statements like inserts or updates or deletes, then it's a good style to mark this function explicitly as being immutable. So immutable means this function will not incur side effects. The function is concerned with computing a value given the parameters that you specify, and will compute a result based on these parameters alone. No changes in the database, no side effects, no state changes. And in indicating this using the optional immutable keyword is assigned to all the readers of your function. The function might be complex, and that it's immutable might not be obvious at all in the beginning. It's also an explicit indication to the rest of the system, to the optimizer, to the query optimizer of the system, that this is a well-behaved true function and it will not incur side effects in the rest of the system, which means that rearrangement of the function codes of these functions, or maybe even caching of results of this particular function, might be a valid thing to do to optimize your queries. Okay. So such UDFs are indeed real database objects. They are stored persistently, just like tables are stored persistently. We can switch off the system and then boot up the database system again, and our functions F will be available again. They are stored persistently and survive the shutdown of the database system. Okay, until we explicitly use drop function to remove the function again. All right. So a few words about the types. So the function f, the sample function f that we've seen on the previous slide, has been a carrier function. So it has k parameters tau I, from which we produce one return value tau here. All right. There's a restriction that all of these tau I, the argument types, have to be atomic types or row types. So no tables in this particular or a set of or something in this particular position. Function arguments have to be atomic or row types, records in a sense. Okay. Function names f have to be unique system-wide, but there is, or database-wide, let's say, but there is limited form of overloading available in PostgreSQL. So as long as this combination, the combination of the function name f and the argument types tau1 to tau k is unique, as long as this combination is unique inside your database, you are fine. Okay, so you could have a function f that takes an int and the Boolean parameter, okay, and a function f of the same name that takes two float parameters, for example. The combination of the function name f and the argument types would be unique, and such overloading would be allowed. There's even a limited form of polymorphism. So a limited form of using type variables, in a sense, in the place of the argument types and also of the return type. But this is really a limited form of polymorphism. We don't have true type variables in the type system of PostgreSQL. What we do have is pseudo types, I would call them, like any element, any array, any enum, or any range. Okay, so any element would stand for any atomic PostgreSQL type that you can imagine. All right, any array would stand for any particular array, so an array of any particular element type. All right, any enum and any range similarly represent some particular enum type and some particular range type. We have met all of these before. So these are not very specific. A function that accepts any element type would work over integers, it would work over booleans, and would be indeed polymorphic in a sense. But be aware, this is really a limited form of polymorphism. There is a caveat here that says, hey, if your function signature mentions any element, for example, more than once, twice, thrice, then all the occurrence of any element indeed represent the same type. Okay, so looking at the signature of this polymorphic function, let me clear the garbage here. The polymorphic function f1, you see that its signature mentions any element twice. Okay, the caveat, the warning sign above, tells us that f1 is indeed a polymorphic function and could be applied at many argument types, but there's a restriction that this any element occurrence for each invocation of f1 indicates the same type. Okay, so wait, let's switch over to a piece of paper to make this more clear. So the type of f1 in Haskell terms would be something like this. So this should be read, this symbol should be read as has type, as in PostgreSQL. The type of f1 should actually in Haskell be noted as this. Okay, right. And as you see, the two occurrences of any element indeed denote the same type. Okay, This is a more polymorphic and more general type, and it's actually not representable using the polymorphic limited polymorphism of PostgreSQL. So this function would indeed accept two tuple components of some arbitrary type here. This is not possible in PostgreSQL. Any occurrence of any element indicates the same type, which is just the function signature above here. Okay, what about F2? F2 promises that it can produce any array, it can consume any array and an integer, and then produce any element. And again, the same caveat applies. The element type of this array has to be the same type as the return type of this function F2. So switching back to our sheet of paper here, this would be the function F2 in Haskell notation. We don't have arrays here, let's talk about lists. So F2 accepts a list of some element type. Okay. It also accepts an integer. As you can see, I'm using tuple notation here. There's no currying in PostgreSQL. We have to consume both arguments at once. And what we would return is not some arbitrary type B or whatever. We would return A. So these two guys have to be the same. So limited form of polymorphism indeed inside PostgreSQL. What this function would probably do is use the integer index to select one particular element from this the first collection from the array or list, and then return that particular element. So the signature of F2 makes sense, but it's not as polymorphic as the signature promises. So this would be something else. It's more general and it's not expressible inside the type system of PostgreSQL. Okay, so that would be a limited form of polymorphism. You don't see that much used much outside there, but it's present, and here and there we have used it to good measure already here in our group, in our teaching, in our research. Maybe it will come. You will come across it in the next few weeks. Okay. So we were talking about restrictions regarding the argument types. Those have to be atomic or they have to be row types. There is no such restriction regarding the return type. Actually, functions f, user-defined functions f, may return tables. So we can have table-valued functions or table-generating functions, just like the set-returning functions that we were talking about in the previous video. Okay, so if this is a possibility, then we have to think hard about the behavior of such a function f. What's the behavior if the final query evaluated inside the body of f, the qn, if you recall, what's the behavior of f if it's an atomic function with an atomic return type, or a table value or table generated or set returning function if the type tau indeed is specified as set of some tau prime? You've seen the set of tau prime notation already in the previous video. So this is the behavior that is implemented inside SQL. So if the final return value defining function qn, if it returns no rows, then an atomic function with an atomic return type would return null. A table generating function would return the empty table, nothing to iterate over. Okay. If qn indeed, this last query, returns many rows, then an atomic function would return the first row. The first row, whatever that means. So qn better defines a well-defined explicit order using order by, for example. Otherwise, returning the first row is a questionable thing to do. Okay. In the case of a table generating function, all rows will be returned. All rows will be returned from the table generating function that we've defined. If Qn, the final query, defines some well-defined order, the evaluation of our now user-defined table generating function will yield these rows in this well-defined order. If we then iterate over the result of our UDFF, we will see the resulting rows in the well-defined order prepared by Qn. Otherwise, all bets are off and we will be iterating over in any order of the result of Qn. So if this is important to you, better make sure that Qn defines a well-defined order that your callers can iterate over. So where may such functions be invoked? Well, if f is an atomic function, we will be able to invoke it wherever such a value v of the return type tau is being expected. That's UDFs can really be inserted everywhere where atomic value of tau is expected. If tau is a table generating function, then we may invoke f everywhere we would iterate or where we would invoke a table in a from clause. So the from clause would iterate over the results of this table generating function, and wherever we would specify a tabular subquery or a tabular or a table inside the from clause, we could also use our user-defined table generating function. We have seen that with the built-in set returning or table generating function like generate series, generate subscript, regex matches, and so on. Okay. As I told you, there is the possibility to have DML statements, so state-changing statements inside the body of such a function. So let's assume that QI, one of the queries in the sequence of SQL queries and SQL statements inside the body, is indeed such an DML statement and invokes updates, state changes on the database. Then, of course, that f here, the user-defined function, is somewhat questionable. So what we have then with f is not really a function anymore because it incurs side effects on the rest of the database. It's then good style, actually it should be a requirement if you ask me, to not use the immutable option, use the volatile option in place instead. Alright, so the volatile option would indicate to the rest of the system and to the readers of your function that indeed the body incurs some side effects on the database. And this means be aware when it comes to the moving this function around in a query, or try to optimize calls to that particular query. Such optimizations, most of the optimizations then are not correct anymore if the function is indeed a state changing function. Maybe it should be called a procedure instead in this case. If your function is all about state changes and you actually are not keen to return any particular value, but if f is really only about state changes, then use void as a return type, which indicates that no usable value is being returned from f. It's all about the state changes. Or if your state changing function is really the last function inside the inside the body of f, so if I here is indeed n, so qi is indeed the last function, then it might be worth to consider to extend this query qi with the returning keyword. We have seen this before in the lecture. The returning keyword can be appended to a SQL DML statement and will of course incur the side effects by this DML statement, but will indeed also return the values of these expressions E1 to Tn for all the rows that have been affected by your DML statements. They will be evaluated for all the rows that have been affected by your DML statement, for example, or the inserted rows or the updated rows. For these, we could evaluate all of these expressions. Their values would be collected in a table, and that table would be returned from the from QN and thus from your user-defined function. Okay, so that's another option to maybe report on how many or which side effects your side effecting function has returned. You can indeed use returning to also report some informative return values to your callers. All right. So here's the first example of a user-defined SQL function. Okay, you can tell these SQL functions from other functions in that the language that we are using to implement the body is indeed the SQL language, and this postfix makes that clear to us. You will see other languages mentioned here when we use PL/SQL or even other programming languages embedded into the database kernel. Then that marker will change here, but for now we are implementing SQL function. The body is pure SQL. The function that we are looking at here is indeed a real function. It's immutable. It will compute the value only based on the argument type that we are supplying. In this case, this is just a text string S, and the return value will be atomic, so it's just an integer. And you've already seen what this function is supposed to do. We could pass a Unicode subscript symbol into this function and then get as the result the decimal value of this particular subscript. So these are characters somewhere scattered in the space of the Unicode code points. This function would translate these subscript symbols into real integer values, which can be used in further computations. And this is the body of the function. Nothing special is going on here. There's many ways to implement this. I think I've brought two possible implementation with me in the editor. We will look at these in a moment. This particular implementation enumerates all the Unicode symbols in this array and will then unnest these. Okay, so we will iterate over these in the order 0, 1 up to 9. Okay, to make this iteration order explicit, we will use with ordinality. Okay, the ordinality would produce this extra column value starting from 1, indicating that 0 is the first in iteration order and the 9 is last in iteration order. So this with ordinality makes iteration order explicit for the rest of the query. Because we are only interested in this particular subscript symbol S, we would select for that and then return its iteration index, the value for this particular subscript symbol. Don't forget to subtract -1 here at this particular point, because we would like to return numbers from 0 to 9, but the iteration index would be counted from 1 to 10. All right, so this is a UDF with atomic return type. If we pass some string S here that is not to be found among the Unicode subscripts, our function subscript will return a null value, which is a reasonable behavior, I would say. So let's quickly switch over to the editor here. And I brought this function subscript with me. Let's first look at the implementation that we've seen on the slide. You see the create function statement with the language SQL and immutable. Oh, whoopsie, that was too much. There we are. The language SQL immutable postfix that we were promising. Okay, so far we have seen that on the slide. When I define functions in the sample files, and I think it's good style to do so, I introduced them by this drop function call, which says, hey, if there's already a subscript function with argument type X text, so recall, we have some overloading here. I'm very specific. I'm talking about the function of this name with this particular argument type. I'm going to define this now. There may only be one function of this particular name with this particular argument type. If it already exists, please remove it first. Recall that functions are persistent and there might be some subscript functions with this particular argument types around already. I want to redefine it at this point. So let's do that. Okay, so create function looks good to me, has been defined. Okay, we could use that now. We could use that now at any place in a query where an integer value is expected. Okay, so the return type of subscript is integer. We could use this function at any place, any query where an integer typed expression is expected. You have seen this particular sample query already. It was parsing this chemical formula, the citrate, using this regular expression, and would then divide the formula into the atom charges and so on. The second match of this this regular expression is matched by this particular part of the regular expression. You see that this indeed extracts such an atom count in this case, and it's a subscript. It's a Unicode subscript. This second match would be a perfect. It would be a perfect argument for our subscript function, which I'm invoking here inside my regular query. Okay, and what we will see is a translation of the Unicode subscripts into usable integer values. There you go. Okay, so this is the result. The 6 and the 5 and the 7 is the result of our subscript function. If we would remove that subscript function, then we would get the query that we've seen in a previous video, and if we execute that, you see that the subscripts have not been translated yet. Okay. So this would be one particular implementation of the subscript function. There is other possible implementations as long as we are only using SQL in the body of these functions. Let me resize that. So this would be a different possible implementation. It's not relying on arrays and the unnest set returning or table generating function. It's just using literal tables in which we pair the subscript with their integer values in really true relational style. We would just iterate over this table, look for the subscript symbol that we are interested in, and then just return the value. Super simple. Let's redefine this just to see that it works. Don't forget the drop function here. There is already a subscript function with argument type text. Okay, so a new implementation of the function is available. We could use it in the same way here down in the query. Okay. Time for another example. In this example, I'm actually defining a function that has a side effect on the database. So it will perform an insert DML statement on the database. And as such, I have marked this as a volatile function. So it's not truly a function, it's a procedure, let's say, that is incurring a side effect on the database. But it's a well-defined side effect, and it's really a wanted side effect. Because what I'm trying to do is to generate unique IDs. Whenever I invoke the new ID function, I want to get hold of a unique ID, a textual ID that is of this particular form. It will contain of some unique identifier here or some unique numeric value, and I can control the prefix of this unique value using my prefix argument here. So this will be generate unique textual IDs that have a predefined prefix controlled by me, but then a unique suffix here that will make the IDs truly unique. And the implementation is really compact. It's indeed using a SQL DML statement, so it's incurring a side effect. The volatile is warranted. So this is in fact an insert statement, and it's also the last statement, the only and the last statement in the function body of our new ID function. And I'm following the advice of indeed using the returning clause here, the returning clause that I've appended to the insert into DML statement to not only incur a side effect, but also to return a well-defined value. Okay, so this new ID function works internally using a so-called issue table, a two-column table in which I will record the unique ID I'm assigning. This is the unique ID part, the suffix, and also a timestamp when this ID has been issued, when it has been generated and been given out to our callers. Okay. You see the timestamp, the when column here is simply generated by invoking this now timestamp. Okay. And the unique ID is actually generated by the system itself. I'm not bothering with this. I'm just saying that, hey, emit the default value for the ID column. And as you can imagine, and we've talked about this before, I've created the issue table with an ID column that is self-generates unique integer IDs. Okay, so we will see the definition of the issue table in the editor in a minute, but this ID column is of type int, generated always as identity. Okay, so I'm not caring about the actual generation of the value, but the system will generate a unique ID value when I insert another row into the issue table. Okay, which ID has been generated? Well, I can use the returning clause here to evaluate this expression for each row that has been inserted into the issue table. Okay, so there's only one row inserted into the issue table, so this underlined expression here will be evaluated exactly once with the prefix that I've specified, and the ID, this is the ID value that has just been inserted, the ID value of the inserted row. This is the unique numeric value. I'm converting that to text so that I can concatenate it to my prefix. This is actually the value I'm going to return. This will return a single row, single column table with the generated ID. And a single row, single column table is just as good as the atomic value inside the cell. This is just the text value I'm returning from the new ID function. So lots of stuff going on. This would be one particular row here inside my issue table. This is a generated ID generated by the system. This is a timestamp generated by the now timestamp. Okay, so let's switch over to the table actually, to the editor actually, and to the table definition. This is my issue table. It's indeed a two-column table. And as I told you, the ID column is generated by the system. It's an int column generated always as identity. Insertions into issue will automatically assign new IDs. This is a timestamp column whose value I can define. Okay, so let's remove the table if it exists and then generate it. So that's our empty table of issued IDs currently. Empty. Oh, one has too much here. Okay, so that's the empty issue table now. And now for the new ID function that we've defined on the slide already. You see it's just a copy of the stuff we've seen on the slides. There it is. Okay, and now let's generate some IDs. Let's issue some IDs in our system. So that would be one particular silly example query. So all of the dinosaurs should become customers of our system, given that they are bipedal or have two legs. Okay, all the two-legged dinosaurs will be new customers in our system. So I will assign to them new customer IDs. You see the prefix of the IDs will be customer, and let's see what comes out of this. We hope that we get unique IDs for all the bipedal dinosaurs that we are admitting as customers in our system. And there you go. There you go. The customer prefix is there. It's the 1, 2, 3, 4, 5, 6, 7. The unique IDs are there. Looks good to me. Okay. And now we could check what's the current state of issuing customers. What are the IDs that have been given out and when did that happen? So let's see what's the current state. So indeed 7 IDs have been given out. They have been given out all at the same time in the context of this very same query, which has been run at one well-defined time. So all of the issues have been done at the same time. But this table issues would keep a protocol of when we have admitted new customers, and that could be useful later for auditing or recurring purposes. So that would be our one example of our volatile function with side effects and using the returning clause. So one final example is called for here, and that would be an example of a table generating UDF, a table generating user-defined function. And you can see one example of such a table generating function here. It's called unnest2. We already have an unnest function that can unnest the elements of any given array. And I would like to have a specific version of that that can actually operate over two-dimensional arrays or over multi-dimensional arrays, and would return the arrays in this particular rectangular array in column major order. Okay, so emit the elements in this rectangular grid in the array that you're specifying, the XSS array, columns first, and not rows first. So we would scan the first column, then a second column, then a third column, and would emit the elements of XSS in this particular order. Okay, so what we would get is a table generating function. And what you can see here is that I'm using the polymorphic conventions supported by PostgreSQL. Okay, so the argument array would be of type any array. So it would be a multi-dimensional array of any argument tau, and I would return a set of any element of the elements tau of this particular array. So indeed, these two polymorphic types are connected to each other. The element type of this array would be just this particular return type in the table, in the generated table. These would be identical, the element type and of the array and the return type, the contain type in this generated table. Okay, so how do we do that? Well, we would just use the first and the second dimension of the multidimensional array and generate all the possible subscripts in the first and second dimension and call these subscripts I and j, and then would order them in a well-defined fashion. So in the second dimension subscripts would determine the order first, the sort order first. So you see it's j, I here. The second dimension, the column dimension, determines the order of returned elements first. And then I would just use the I and j indices in the first and second dimension and access these elements in the array XSS, and this is the returned order. And the order is the returned elements, and the order of the returned elements is well defined. It's well defined by this order by clause. This table generating function will emit these elements in this particular well-defined order. When we iterate over the results of this set returning or table generating functions, we will see the results in this well-defined order. Okay, so you see this polymorphism really is very, very basic. Actually, my intention indeed had been to give unnest to this particular type. It should work over two-dimensional arrays. Okay, so I'm very specific about the dimensions here, and I'm specific about the element type that is coming in here and going out of here. This would be a much better type. Sadly, such specific type language is not available in PostgreSQL. We have to live with that, but for this particular use case, it would just work fine. Okay, so let's see. I think I have the example with me here. So this is the unnest2 function, and it looks just like on the slide. So let's just define it. Okay, and that would be a sample use. So we would call unnest2, and we would place that call inside the from clause, which makes sense because unnest2 is a table generating function. We can iterate over the results of the rows that are generated by unnest2 in a well-defined order. Okay. Okay, cool. And the argument of unnest2 is indeed a two-dimensional array. And it's my intention to return the elements of this array in column major order. So we would walk down the first column, ADX, then BE, Y, CFZ, and that would be the order of the elements I'm trying to return here. Let's make the order in which we are iterating over these results really explicit in the output of this query using with ordinality, and then we will see that indeed A, D, X, the first column values have been produced first, and B, E, Y have been produced on the 4th, 5th, and 2nd position, and so on. Okay, looks good to me. So now see what would happen if we would if we would remove this order by J, Y. Explicit ordering here, redefine the function. Okay, so now what comes out of this particular query has some order, but not a well-defined order. The system would be free to rearrange and to rearrange the order of the results, and I think we should be able to observe this when we reevaluate the function here. Yeah, indeed, A, B, C are now on at positions 1, 2, 3, so that would be row major order, which could also be a very useful order, and we could redefine our uns2 function to really return the results in row major order. That would be the way to do it, but we wanted column major order, so let's switch back to that and repair the function. Okay, so one final word on the return type of such table generating functions. If the rows inside your return tables are of indeed are of complex row types, not of atomic types, then of course there's the question of how would the individual columns of these rows be named, and what would be the types of the individual columns that your return tables contain. So this is not a question if the return type is a table of atomic values. This is this particular leftmost case here on the slide. If your return type tau is indeed set of tau prime, where tau prime is atomic, what you would generate is this single column table, and everything is fine. Okay, but if your return type tau is indeed set of tau prime, where tau prime is a row type, then you better have a row type defined that is using explicit column names and explicit column types. What you that would then emit from F is a well-defined table with M columns that are properly named and are of course properly typed. Alternative syntax would be the rightmost syntax here, where tau is indeed specified as table C1 to Cm, where each of the M columns has also a well-defined type. I think I like this particular syntax best. If you already have predefined row types tau prime, then this is the way to go. But if you really need to specify a one-off return type for your table generating function, I think this would be the most intuitive and I think the nicest and elegant syntax. F returns a table of M columns, and the M columns will have types tau1 to tau m. Okay. All right, we will see many examples of this in your assignment sheets and also in the further course. All of this will make sense when you see further examples. I think that's about it. That's our discussion of user-defined functions. Okay, a very versatile and very powerful tool to abstract functionality, to encapsulate it in the body of a function. We will see this used many, many times to good measure in the upcoming weeks. Okay, see you then. Take care. Bye.